1.5 is about differentiation techniques, the power and sum difference rules. So we have a new notation called the Leibniz notation. When y is a function of x, we will also designate the derivative f prime of x as dy over dx, which is read the derivative of y with respect to x. The first rule we're going to talk about is the power rule. So for any real number k, if y equals x to the k, then the derivative with respect to x of x to the k is just k times x minus 1. So we're bringing the power out front, and then we subtract the exponent by 1. So to differentiate y equals x to the fifth, the derivative with respect to x of x to the fifth, we bring the power out front, so the 5 comes out front, times x, and then we subtract 1 from the power. And so we end up with 5x to the fourth. If you did the long formula with finding the limit, you would get the exact same thing. So now we're teaching the shortcut so that you can find the derivative more simply and quicker. So let's try this with y equals x. The derivative with respect to x of x, remember there's always that invisible power of 1 written. So we bring the 1 power up front, and we subtract 1 from the power, but that's just 1 times x to the 0, and x to the 0 is 1, and so we end up with just plain old 1. The derivative with respect to x of x to the negative 4, we bring the power up front, so negative 4 times x to the negative 4 minus 1, but that's just negative 4x to the negative 5. Let's go ahead and try 2 more. Same idea. So the derivative with respect to x of x to the 15th is 15 times x to the 15 minus 1, or 15x to the 14. The derivative of x to the negative 7, we bring the negative 7 out front, and then we subtract 1 from it. So we end up with negative 7 x to the negative 8. Now, why is the derivative with respect to x of pi squared equal to 0 and not 2 pi? Now, pi is a constant and not a variable. It's just a never-ending constant. And the derivative of any constant is 0. Let's try one that's a little bit more tricky. Y equals the square root of x. So that's the derivative with respect to x of the square root of x. But we can rewrite this with using the power of 1/2. And so this works the same way. We pull that 1/2 out front, and then we subtract by 1. And so we end up getting 1/2 x to the negative 1/2 or we can rewrite this as 1 over 2x to the 1/2 or 1 over 2 times the square root of x. Let's try x to the 0.7. So the derivative with respect to x of x to the 0.7, we bring the 0.7 out front, and then we subtract 1 from it. So we end up with 0.7x to the negative 0.3. We already talked about this a little bit with the pi notation. The derivative of a constant function is 0. Automatically. The derivative of a constant times a function is the constant times the derivative of the function. Using derivative notation, all we're doing is we pull the constant out front, and then we take the derivative like we've already been doing. So the derivative of 7x to the 4th, we can pull that 7 out front and then find the derivative of x to the 4th. So that's 7 times 4, x to the 4 minus 1, or we got 28 x cubed. The derivative of 9x, we can pull that negative 9 up front, and then we're going to do the derivative of x. Well, that's negative 9. Remember, there's always a power of 1 written, so we pull the 1 up front, and we subtract 1 from it. And so we get negative 9x to the 0, which is negative 9 times 1, or just negative 9. The derivative of 1 over 5x squared, we can pull the 1/5 out front and then find the derivative of x squared, or 1 over x squared. But that can be rewritten as x to the negative 2. And so we got 1/5 times negative 2, x to the negative 2 minus 1, or what we really have is negative 2/5, x to the negative 3, or we can write that as negative 2/5, 2 over 5, x cubed. The next rule is the sum difference rule. So the derivative of a sum is just the sum of the derivatives. So we find the derivative of each piece and then we add them together when we're done. Same thing goes for the difference. I find the derivatives of each term or each function and then I subtract them. So we can find each of the following derivatives. The derivative of 5x cubed minus 7. So we're going to find the derivative with respect to x of 5x cubed minus the derivative with respect to x of 7. Well, that's going to be 5 times the derivative of x cubed And the derivative of a constant is 0. So that derivative of 7 is going to be 0. So we have 5 times 3x to the 3 minus 1, which is 15x squared. So the derivative of that whole function, 5x cubed minus 7, is just 15x squared. Let's try another one. We're taking the derivative of 24x minus the square root of x plus 5 over x. So we're going to find the derivative of each piece. The derivative of 24x minus the derivative of the square root of x plus the derivative of 5 over x. We can pull that 24 out front and just find the derivative of x. We can rewrite the square root of x as x to the 1/2. And then we can pull this 5 out front and rewrite 1 over x as x to the negative 1. And so the derivative of x is just 1x to the 1 minus 1 minus 1/2 x to the 1/2 minus 1 plus 5 times negative 1 x to the negative 1 minus 1. And so what we end up with is 24 minus 1/2 x to the negative 1/2 minus 5x to the negative 2. Or we can write this as 24 minus 1 over 2 square root of x minus 5 over x squared. And let's differentiate one more. So we have y equals 3x to the 5th plus 2 cube root of x plus 1 over 3x squared plus the square root of 5. So we're going to find the derivative of each piece. So let's pull the 3 out first and then find the derivative of x to the 5th. Let's pull the 2 out and find the derivative, and we're going to write this as x to the 1/3. Let's pull this 1/3 out and rewrite this as the derivative of x to the negative 2, and then plus the derivative of the square root of 5. So we have 3 times 5x to the 5 minus 1 plus 2 times 1/3 x to the 1/3 minus 1 plus 1/3 times negative 2 x to the negative 2 plus 1, 2 minus 1, and the derivative of a constant is 0. So we get 15 x to the 4th plus 2/3 x to the negative 2/3 minus 2/3 x to the negative 3, which can be written as 15x to the fourth plus 2 over 3 cube root of x squared minus 2 over 3x cubed. Final answer. So it's important to be able to determine points at which the tangent line to a curve has a certain slope, that is, points at which the derivative attains a certain value. So we want to find the points on the graph of f of x equals negative x cubed plus 6x squared, at which the tangent line is horizontal. So let's recall that the derivative is the slope of the tangent line and the slope of a horizontal line is 0. So we need to find all the points on the graph where the derivative of f equals 0. So really what we're looking for is f prime of x equals 0. So f prime of x, we're going to find the derivative of negative x cubed plus the derivative of 6x squared. So we're going to pull that negative out front times the derivative of x cubed. And we're going to pull that 6 out front and find the derivative of x squared. So we end up with negative 1 times 3x squared plus 6 times 2x, or negative 3x squared plus 12x. Let's set that equal to 0. Negative 3x squared plus 12x equals 0. Well, we can take a negative 3x out of both pieces, and we're left with x plus 4 equals 0. And so we get negative 3x equals 0, or x equals 0. And we also get x plus 4 equals 0, or x equals negative 4. I'm so sorry, this should be x minus 4 because we pulled out a negative 3, and so you should have a positive 4. So now that we found our x values, we just want to plug them back into the original function to find the y values, and that will give us our points. So coming up to the top, we got f of 0, which is negative 0 cubed, plus 6 times 0 squared, which is 0, and f of 4, negative 4 cubed, plus 6 times 4 squared, which gives me 32. And so our 2 points are at 0, 0, and 4, 32. And example 8 is very similar, except we're using the same function, but we're looking for the tangent line that has a slope of 6. And so instead of setting that derivative equal to 0, we're going to set it equal to 6. it's going to have the same exact derivative, which we already found, was negative 3x squared plus 12x. And so let's go ahead and set that equal to 0. I'm sorry, to 6. Which we then have to set equal to 0. Well, my GCF, we can pull out a negative 3. We're left with x squared minus 4x plus 2. We can divide both sides by negative 3. So we get x squared minus 4x plus 2 equals 0. We're going to have to use the quadratic formula to solve this. So we have 4 plus or minus the square root of 4 squared negative 4 squared minus 4 times 1 times 2 all over 2. That's 4 plus or minus the square root of 16 minus 8 all over 2. And so we get 4 plus or minus the square root of 8 all over 2. Or 4 plus or minus 2 square root of 2 all over 2. We can take a 2 out of the top, and we're left with 2 plus or minus square root of 2 all over 2. The 2's will cancel, and we get 2 plus or minus square root of 2. So we need to plug these values into our original function. So let's plug in the first one, 2 plus the square root of 2. So f of 2 plus the square root of 2 equals negative 2 plus the square root of 2 cubed plus 6 times 2 plus the square root of 2 squared. So we get negative 8 plus 12 square root of 2 plus 12 plus 2 square root of 2 plus 6 times 4 plus 4 root 2 plus 2. And so we get negative 20 minus 14 square root of 2 plus 36 plus 24 square root of 2, which gives me 16 plus 10 square root of 2. So the only thing that changes when we plug in f of 2 minus root 2 is we get 16 minus 10 square root of 2. And so my 2 points are 2 plus square root of 2, comma 16 plus 10 root 2, and 2 minus square root of 2, 16 minus 10 square root of 2.